Rounding is one of the most common operations in data representation. It is also one of the most underestimated. Rounding changes data not by removing it entirely, but by reshaping it. The value remains, but its exact form is altered. And that alteration has consequences. A useful metaphor for rounding is sanding a surface. When you sand wood, you do not cut off entire sections. Instead, you smooth away fine details. The shape remains recognizable, but sharp edges disappear. With enough sanding, subtle features are lost. Rounding works the same way with data. So what is rounding? Rounding is the process of replacing a value with a nearby representable value, according to a defined rule. Instead of discarding information outright, rounding approximates it. For example, a value of 3.7 might be rounded to 4, or to 3.5, or to 3.75, depending on the rounding method and the target representation. Rounding is different from truncation. Truncation cuts off data at a boundary. Rounding shifts data toward the nearest, allowed value. The result is closer to the original, but still not exact. How does rounding occur? Rounding appears whenever a value must be represented with limited precision. This happens during numeric formatting, type conversion, aggregation, serialization, and storage. It also occurs implicitly in floating-point arithmetic, where results must be mapped back into a finite representable set. There are many rounding rules: round half up, round half down, round half to even, floor, ceiling, and stochastic rounding all behave differently. Each rule introduces its own pattern of error. These rules matter because rounding errors are not random unless explicitly designed to be. Why do systems rely on rounding? The primary reason is that most real-world values cannot be represented exactly in finite systems. Decimals often have infinite binary expansions. Measurements are continuous. Computation produces intermediate results with more precision than storage allows. Rounding is the mechanism that reconciles infinite precision with finite representation. It is also used to improve usability. Rounded values are easier to read, easier to communicate, and often sufficient for decision-making. Precision beyond a certain point provides diminishing returns. However, rounding always introduces error. This error may be small, but it is systematic. Rounding has several defining features. First, it preserves scale but alters detail. Magnitudes remain similar, but fine distinctions disappear. Second, rounding error can accumulate. Repeated operations amplify small deviations, especially in iterative calculations. Third, rounding can introduce bias. Some rounding rules consistently push values upward or downward. Others distribute error more evenly, but at the cost of complexity. Finally, rounding interacts with aggregation. Summing rounded values produces different results than rounding summed values. The order of operations matters, and this can lead to discrepancies that are difficult to explain without understanding representation effects. The implications of rounding are significant. In analytics, rounding affects totals, averages, and rankings. In finance, it influences pricing, interest calculations, and compliance. In scientific computing, it constrains accuracy and reproducibility. In machine learning, rounding affects feature values, gradients, and convergence behavior. Small distortions at scale can alter model outcomes. Perhaps most importantly, rounding shapes trust. When results differ slightly across systems or runs, rounding is often the cause. Without awareness of rounding effects, these differences appear arbitrary. Professional data systems treat rounding as a controlled operation. They choose rounding rules deliberately. They apply them consistently. They document when and where rounding occurs. Because rounding is not just a formatting choice, it is a representational decision that determines which details survive and which are smoothed away. And once those details are gone, they cannot be recovered.